Get it going. Good afternoon, everyone, and welcome to today's joint asset colloquium along with Infosys condensed matter colloquium. So thanks firstly to Professor Vijayaraghavan for making this possible, and also welcome Professor Florian to today's colloquium, and also to this nice institute. I hope you had good interactions both with faculties and students. And without taking more of your time, I now therefore request Professor Vijayaraghavan to formally introduce today's speaker and conduct the rest of the proceedings.
Thank you, Satya. Welcome, everyone. Just a very quick word. The Infosys Condensed Matter program is supported by a grant from the Infosys Foundation, and it's been now several years. And because of the timing, we decided to combine it with assets. So thank you, Satya, for doing that. This way, we are able to reach out to a wider audience. So Professor Florian is a theoretical physicist and mostly working at the intersection of nanophysics and quantum optics. So today, he's going to be telling us about using machine learning techniques in physics, and particularly in applications in quantum computers. Florian received his PhD from the University of Basel, where he worked with Professor Bruder. He initially did a short postdoc there and then continued to Professor Steve Gervin's group at Yale. That's actually where I met him. I was a PhD student and we overlapped for a couple of years. So I've known Florian for a while. And then he joined Ludwig Maximilians University in 2005 as a junior research group leader. And then since 2010, he was full professor at the University of Erlangen in Nuremberg. And since 2016, he's the scientific director of the Max Planck Institute for Science of Light in Erlangen. So it's great to have you, Florian, here, and we look forward to your talk. So welcome. Over to you.
Okay, great. So thank you very much for the kind introduction. Thank you, Vijay, for hosting me here. I already had, do we have an echo? I already had great discussions this morning with people here. And in the following, I'll tell you something about what we started, say, in 2016, 2017. So we asked ourselves, can we use all these great new deep neural network techniques that were evolving in the area of computer science and apply them to physics, especially to quantum physics? So that will be the purpose of today's talk. I want to start in a very general manner, and that is by talking about the brain. So if you think about your brain, you can view it in many ways, but one way to view it is to treat it like an information processing machine. So there is an input coming in, like the image you see or the sound you receive. Then your brain processes this input, and afterwards there will be some output. For example, you will say some word or you will take some action. So that's the output. Now, one of the amazing aspects of this information processing machine is that it's extremely flexible and robust and can deal with very large varieties of data. For example, it can see a picture of a light bulb with a shape and in an angle that it has never seen before, and yet instantly recognize this picture as being a light bulb. And that's very amazing from the point of view of, say, a software developer, because if you wanted to hard code a program that is able to do the same task, it's basically impossible. A hard-coded algorithm that would recognize all of these differently shaped light bulbs. So what's behind it, you ask? And we can look inside the brain, and since about 100 years, we have explored how the brain works. And inside the brain, of course, are just biological cells, the neurons, and they are connected in a large, deep network of connections, and they send to each other electrical pulses. And we have also learned by now that during life, these connections change, and that is how we learn. So the questions come up, can we do the same using computers? Can we implement the same in an artificial manner, creating what would be an artificial neural network? And this question has first been raised even at the end of the 50s, so more than half a century ago. The idea would be that an artificial neural network, just like the biological neural network, would consist of neurons. These are the circles in this picture. But these neurons in the artificial neural network are much, much simpler than your biological neurons. So in contrast to biological neurons, at any given time, one of these artificial neurons is only described by a single number. The number indicates how strongly it is activated. And then the idea would be that these neurons are typically arranged in layers and they are connected with connections of variable strength. And then in the end, the idea would be that you feed in your input as a vector of values into the input layer, and then step by step, layer by layer, in a sequence of very simple calculational steps, you calculate what would be the values of all the other neurons inside this artificial neural network, and eventually what would be the values of the neurons at the uppermost layer, which is the output layer that represents the answer that the neural network gives you for a particular input. So for example, if the input is an image, then the input neuron values would be the grayscale values of all the pixels in the image, and the output neuron values might indicate what type of image the neural network thinks you're looking at. For example, if the right neuron lights up and has a high activation value, then you would think it's a cat, and if it's the other neuron that lights up, it's a dog. Okay. Now, the goal is still the same. So you should be able to take in an arbitrary image and quickly recognize it, even if you have never seen before this particular image. So the question is how to do that. And the secret behind it is to properly arrange the weights, the connection strengths inside the network. But instead of you fine-tuning these connection strengths by hand, instead you have many, many training examples on the order of millions of training examples. And for each of these examples, you not only know the input, but also the correct output that should emerge. And then for each of these, you slightly adapt the weights so that you come a little bit closer to the correct output. And eventually your neural network will have been tuned up so as to give the correct outputs. Okay. So this has been around, this idea has been around for more than half a century, and there have been ups and downs. But the real breakthrough came about 10 years ago, because that was the first time that a neural network, many layers, was able to beat all the other approaches in image recognition. So it was able to win this so-called ImageNet competition, where you're given 1 million training pictures, and then you can do whatever you want using your algorithm. And then afterwards, you're tested on images that you haven't seen before. And since then, neural networks have been better than humans in image recognition and also in many other tasks by now. Now, if you're interested, there's much, much more to say, of course. If you're interested in this, there are many great lectures on the web that you can watch. I myself contributed some lectures that are geared towards physics students. So if you have the typical math background of a physics student after the first or second year, like linear algebra, then you should have an easy time, say, watching this lecture series, Machine Learning for Physicists, that you can find on YouTube. And then later I also put up there a more advanced mathematical conceptual lecture. That's the advanced class. Okay, so I just wanted to point this out. And then before I jump into the main topic of the talk, I just briefly want to mention the activities in our group beyond what I will be talking about in the following. So in the last few years, we really have focused on applying machine learning to physics. We are at the Max Planck Institute for the Science of Light. So we are interested in how light propagates, for example, in so-called photonic crystal structures, where you can engineer some band structure for electromagnetic waves. And we have, for example, used machine learning to optimize such photonic crystal structures. Here on the right, you see another topic that is of interest to us. So we call it artificial scientific discovery. The idea would be that you want to train a computer to behave a little bit like a scientist. So coming up with a hypothesis, finding the most economical way to test the hypothesis, and then analyzing the incoming data from the experiment and maybe refining your hypothesis and so on. And one of the tasks we solved recently, or we contributed to, was how to discover smart collective coordinates. If you have a very complex system, how can you extract the essence of the system? Then we also like to turn the question around. Instead of saying, what can machine learning do for physics? We ask, what can physics do for machine learning? And so that falls under the domain that is sometimes called neuromorphic computing. So imagine some complicated physical system like a nonlinear optical setup, and you want to send in some input, get some output, and maybe tune up the system so as to get the right input-output relation. How could you do this, for example, by physical means of training such a system? And we have some ideas on this. And the hope being that, of course, in the end, you will end up with something that has much less energy consumption and is much more rapid in its processing than what you would otherwise have in artificial digital neural networks. So these are some of the topics, but today I want to focus on this machine learning for quantum technology, which has kept us busy over the years. Now, here's the setting. So you imagine you have one of these emerging quantum computers containing many individual quantum systems that you can very well control. That's a lot of complexity, and there's many things to think about. For example, how to fight against noise and how to set up the quantum calculation in the most efficient manner. So in order to do that, maybe classical machine learning could help us. If we connect a classical neural network to that device, maybe it helps us to optimize the quantum computer. And when I say classical machine learning, it's just to distinguish it from the also emerging field of quantum machine learning, where the idea is that you could maybe even on top of that speed up the operation of something like a neural network by using quantum effects. So today we're only using classical machine learning on quantum devices. Okay. Now, the particular machine learning technique that I will be talking about today is actually called reinforcement learning. And to put it in a nutshell, it's about discovering strategies. I will explain more what that means in a moment, but it's obviously a good task for applying this to quantum devices if you are able to discover a good strategy to control and manipulate the quantum device so as to obtain a desired output. So that's reinforcement learning in a nutshell. But I want to contrast it to what you typically do for neural networks. Typically, what you do is what I told you about already. You have these millions of training examples, the input together with the correct output or the label of the image. And that is called supervised learning because you're learning under supervision of a teacher who knows all the correct question-answer pairs. And then hopefully, after absorbing this information, the student eventually will be able to imitate the teacher or slightly extrapolate from what the teacher has been telling. Now, there's a catch. Maybe you will never get really better than the teacher in this manner. And so the question is, if you want to be a very smart student or want to be a scientist, how do you learn new things? And well, there is basically only one way to explore new stuff at first, which is trial and error. Yeah? You try out something, it doesn't work, you try out the next thing. Maybe it works a little bit, and then maybe you stick to that and try to modify it. Eventually, it will start to work better, and so you go on. So that's trial and error. And that is the basic principle of reinforcement learning. You are trying out something. If it works, you modify it, and you are reinforcing the good actions that you have taken over time. And so then hopefully maybe the final level is unlimited. Now, famously, reinforcement learning as a technique has been applied to great success in the past few years. One aspect, one example that went through the media was the neural network being trained to beat even the best human players in the rather complex board game of Go. That was an example of deep reinforcement learning. So reinforcement learning based on deep neural networks. Now, coming back to the concept, if you ask a computer science person about reinforcement learning, they would probably draw this diagram. So we subdivide everything into two pieces. One of the pieces is the so-called environment. That's really the world you are dealing with. In our case, later it will be the quantum device. And the other part will be the so-called agent. Think of a robot or a neural network whose purpose is to do something inside this environment. And the basic idea is that the agent takes in observations and then based on these observations tries to suggest the next action. And this action might here be to move one of these blocks. And then the cycle continues. So always an observation comes in, you suggest the next action and so on until you are satisfied with the result. Now this mapping from observation to the suggested action, that is called the policy. That's, so to speak, your strategy. That's how you proceed in the world, how the agent proceeds. And our goal will be to optimize this policy. How do we want to optimize this policy? Well, we, the end user, the human, so to speak, we have to define what is our goal. And we will encode this goal by writing down a reward. In this particular case, we could say you get a higher reward if you stack many blocks above each other, then the reward will be high. And then the goal will be to improve the policy so as to get a very high reward. So that's the basic nutshell of what is reinforcement learning. So by the way, you are always invited, of course, to ask any questions also during the talk. Please, yes. Yes, yes.
And whenever you're doing an optimization of this kind, there's a possibility that you'll fall into a local minimum, which is not the best possible.
Yes.
Could be shallow. Does this happen?
Yes. So yeah, so absolutely. That's the first question to ask. Can we get trapped in a local optimum? And the answer is absolutely yes. Sometimes this is avoided because the whole process I will explain is a bit stochastic, so that sometimes helps to escape the local optima. But definitely, in spite of this, you can get trapped in local optima. And then if that is a serious issue, and it depends very much on the scenario, then of course you have the ability to run it several times and maybe take the best of 10 runs. But that is always an issue. Another way to remedy the situation could also be that you engineer your reward function, because even for one and the same task, there are many possible choices of a good reward function that encodes the task. And some of them may be better for the purpose of training than others. Yeah, but it's important.
So the question here is really, I mean, these are usual problems, usual kinds of solutions. But the question here is, how pliable is the policy? How do you program a policy?
How reliable is the...
How easily can you change the policy?
Oh, yeah, how pliable. Sorry. So I will say it in a moment, but the policy is typically then encoded in these more modern approaches as a neural network. And in that sense, it can be as expressive, as powerful as you like. So it can take in whole images and then suggest actions. So eventually, if you make it large enough, in principle, it could encode arbitrary policies, but the question is whether it reaches that optimum policy.
Therefore, hard to think about.
Yes, yeah. Good. Okay, fine. So then if there's no further question at this point, this is the general setting of reinforcement learning, but there's an important distinction also to make with regards to the environment, the world around you. Namely, the question is, do you have a model or you don't have a model of the environment? Can you simulate it or not? Depending on that, we speak of model-free reinforcement learning, where we treat the environment as a black box, or model-based reinforcement learning, where we do know the evolution equations. And they have both their advantages and disadvantages. I will first talk about model-free reinforcement learning. This is something that also can be easily then applied to experiments where you maybe don't know all the detailed parameters of your device and still want to apply this set of techniques. Okay, so some few more words about this particular set of model-free reinforcement learning. So the question is, how do you encode this policy to map an observed state to the next suggested action? And there are different branches of model-free reinforcement learning, basically two big branches. And I'll just, for the sake of brevity, mention one of them here, namely so-called policy-based policy gradient techniques. And so the idea here would be that the policy, the strategy, is something probabilistic. So if you give me a state S, I will not suggest deterministically a particular action, but instead I will suggest a probability distribution over possible actions. The advantage being that probabilities are continuous, and when you later want to optimize your policy, it's much easier to update these continuous probabilities as opposed to discrete choices of actions. And then what you do is surprisingly simple. So you look at the total reward. You have to average it over many runs of this action observation sequence, because everything is stochastic anyway. And what you do is simply gradient ascent. So the reward does depend on the policy, obviously. If you change the policy, you will change the average reward. And the policy has been parametrized with these parameters that I like to call theta here. These might be the parameters inside a neural network. And all you do is to do gradient ascent. So you move in the direction, you move the parameters in the direction where you expect the largest increase of the average reward. And if you work this out, you find, aha, you have to take these gradients of the logarithm of the policy probabilities along the trajectory. And then this tells you how to update your parameters. That's a fairly old algorithm, as you can see here. And yet it's at the heart of much of what is done in terms of reinforcement learning also these days, and has been supplemented by using deep neural networks for this parameterized policy as opposed to the simpler approaches that people used in earlier times. Okay, so just wanted to give a glimpse of what goes on behind the scenes. And now I'll move. Yes, please, there's already a question.
So about deep reinforcement learning, what does deep mean in a more?
Yes. So whenever we talk about deep neural networks, this simply means we have a neural network with many layers. And it turns out these are more powerful than if you have only, say, a single hidden layer between input and output. And the reason seems to be that these are like a very recursive function. So a function of a function of a function of a function. And they seem to be more expressive or seem to be more adapted to the typical problems we have. So for example, in image processing, the lowest layer will detect edges and so on. The next layer, maybe the orientation. This is actually also what happens in our brain, and then goes on and on to higher and higher concepts as you go up the layers. And here it would then refer to using such deep neural networks inside reinforcement learning.
Sorry, Florian, just to follow up here is there a threshold? So 3 is not deep. Anything beyond 3 is deep, or
I will not even comment on this. So people use this in many different ways.
Okay.
So yeah.
But what would be the number for a typical deep network? Like hundreds?
People have really taken hundreds, but even if you have 5 or 10, you would already consider it deep in the sense it's not just one single hidden layer. So it can already be quite powerful. So let me move to the first example here, and that's something that we did a few years back. It was actually when we entered this field of machine learning, and we picked up reinforcement learning, which had not yet been applied to any quantum physics problem, and we wanted to apply it there. And so we asked ourselves, what would be a good example to apply reinforcement learning? And if you have followed closely the discussion, you see this is really a feedback problem. You have an observation coming in, and then the agent decides what should be the next action. So we are really doing feedback. So you want to look out for a quantum physics problem where feedback is important, where measurements come in and then decisions are being taken. Now, among all the possible feedback problems, quantum error correction is a very prominent one and very relevant these days, and also sufficiently complex. So we chose that. And so the setting we have in mind now is we have a small number of physical qubits. They are connected in some fashion. You can do quantum operations on them, but they are subject to noise, as always. And so that leads to decoherence, that leads to decay. And we want to protect the quantum information stored inside the small number of qubits against the noise. So that's a typical setting that we might consider. Now, phrasing it in the reinforcement learning language, here's the picture you would get. The environment is really the qubits plus the noise, so everything, the physical device with everything. And then you would take in measurements, which in this case would be real quantum measurements of a qubit. And the measurement results would be fed into a neural network. The neural network's task would again be to suggest the different action probabilities. Now, what are the actions in this case? Well, in this case, the actions that you can take are quantum gates, so unitary operations acting on 1 or 2 qubits, plus potentially you want to do the next measurement. So that's not a unitary operation, but that's another action you can take. And then the idea is really to try out different actions and improve your strategy. I still have to tell you about what is the exact goal of the game. So let's discuss this. So this is our setting again. And what we want to imagine is that one of these physical qubits has been initialized in an arbitrary unknown quantum state, like a superposition shown here. And it's important that it's really unknown also to us. So we're not talking about stabilizing this particular given quantum state, but any unknown quantum state that might be stored inside the air. So that's quantum error correction as opposed to state stabilization. Now, when the agent starts to do things, it just will randomly apply quantum operations to this device. And to visualize this, I plot a quantum circuit. So time runs to the right. Each line represents a qubit. Inside one of the qubits, we have initially the unknown quantum state. And now the actions you apply could be, for example, controlled not. So you flip the second qubit depending on the state of the first one. So that's an allowed operation. and maybe you do this multiple times, but then you remember that one of the other actions you can take is also to do a measurement. So if I now apply a measurement here, it turns out that this was a very bad decision. Because if you followed this closely, you will realize that by these multiple controlled knot operations, I have entangled all of my qubits. And if I now measure only one of them, I will completely collapse the superposition and I have destroyed my quantum information instead of preserving it. But I should say this is really the situation that the agent is in at the beginning. It just does stupid trial and error at the very beginning. Now, I should also mention briefly what should be the reward. So the simplest way you can set up the reward for this task would be to say, let me look at the quantum state of this particular physical qubit at the end of the time evolution. And let me take the overlap with the initial state. And if this remains high, then I have preserved the quantum information. So that would mean that you're trying to learn both the encoding and then the error correction at intermediate times and maybe the decoding. We have in actual fact invented quite a bit better reward schemes to speed up the training, but that would be the simple idea here. Now, initially, as I said, the agent really does random stuff, and that is shown here in the upper trace, where the quantum information easily collapses. That's when this blue area finishes. But eventually it becomes better and better, and really it avoids these catastrophic measurements. It does find ways to encode the quantum information by repeated controlled knots, so it spreads the information over 3 qubits, and eventually discovers or rediscovers what we would know is the repetition code of quantum error correction. It then also discovers that measurements are not all that bad if you do them in a smart way. So it sets aside one of the 4 qubits as what we would call an ancilla qubit. Of course, the computer doesn't know any of these concepts. And it then starts to apply controlled knot operations and measure the ancilla qubit so as to detect the parity of other qubits. And we know this is a good thing to do in quantum error correction, because if all the parities, so the relative state of the qubits are correct, then also the overall state is correct. And then eventually it applies this whole scheme periodically and can also figure out what to do if one of these parity detections reveals that something has gone wrong. Once this works for a particular setup, the advantage is you can also apply it to different topologies and different qubit setups. So I've shown here several different connectivities, and you could also try different gate sets and different measurements at different qubits. And you see here that every time it discovers a particular strategy that is suitable for this setting. And what is shown in this red box, for example, would be a situation where one of the measurements indicates that something has gone wrong. And then suddenly the sequence has to change, because now it has to figure out what exactly has gone wrong. Is one of the qubits flipped, or maybe is just the ancilla measurement wrong, and so on. So it discovers this whole extra sequence also on top of everything. And then you can do comparisons. You can say, these different approaches for the different connectivities, how much did they improve my coherence times? And you can ask similar questions. You can also then choose different noise models and let it invent new strategies for other noise models. For example, if there's global noise acting on all the qubits, it will invent yet different strategies. So that was very nice. And it also is something we are continuing on now. I don't have slides here, but we're moving to larger qubit numbers. In that case, we are injecting more of our physics knowledge. So here, everything was invented from scratch, and we pretended we don't know how quantum error correction works. If we pay the price of being somewhat less flexible, we can go to much larger qubit numbers, up to 20 right now, in order to discover good encodings given a gate set and so on, and using fast simulators that work in this particular regime. But that is work that is ongoing.
So one of the things you mentioned is that it also decides to have an ancilla qubit.
Yeah.
I mean, it's probably not relevant so much to the operation, but does it choose the same qubit as the ancilla every time, or is it randomly?
No, that's okay. That's a good question. So no, it doesn't. So that is, so to speak, an arbitrarily broken symmetry. Also, it does some funny things if you go inside and analyze it very closely. In one of these cases, I think it may have been this one, it figures out that it may be advantageous to interchange the roles. So during one time span, say qubit number 3 is the ancilla, but then after some swaps and so on, qubit number 4 becomes the ancilla. And apparently it uses less gates if it does this kind of funny swapping where the ancilla is.
And that would again depend on the connectivity of the.
That does depend on the
That's right.
connectivity
Yeah.
and whether you have a linear chain and so on. So it can become quite smart. It also discovers immediately things like if it needs, say, swap gates, because, for example, here we didn't provide swap gates, only C0 gates, it then discovers on the fly the decomposition of a swap gate that it needs into C0s and so on. So it really started from scratch, but that also means it has a harder task, of course. And so we want to avoid that a little bit right now. Yes.
Keep the connectivity same or the topology same, but you just scale it up. Do the strategies change, or it's just a kind of same sequence kind of scaled up by some?
Very good
number?
question. So here we were stuck with 4 or 5 qubits. So because we do everything from scratch, we couldn't really scale up. And the more recent results, we do scale up, but I don't think we have a systematic analysis of how the strategies work. You have to see, you run it 3 times. It could be that you discover 3 somewhat different strategies. Maybe they have all a similar reward, yeah, but they can still look different because there's some degeneracy in what you can do. Oops, yeah, okay. I think.
Yeah, so you mentioned that this error correction was, we have to do it for an arbitrary quantum state. But you also mentioned that the reward function is constructed by checking the overlap with the state. So
Yeah.
if you do not know how to prepare the state, how do you construct this goal function during an optimization?
So the idea is here, in my simulation, I inject a random state, but so to speak, the agent doesn't know the state. So it has to apply a sequence that is really independent of this knowledge. And then later I ask, okay, whatever comes out, how much overlap does it have with the state that I know, but this agent doesn't know? And so that works. Yeah. There's some extra tricky technical details behind it, but we can talk offline about this. Yes.
How often can you? How often is can you improve the result by hand after looking at the result?
Aha. So you mean if I were to look at this sequence and then say, aha, that gives me an idea, but maybe let's, we haven't really asked the question like this. We have tried to interpret it, all these sequences, so that already gave us some insights. But what we can spot by hand, so to speak, is that sometimes these sequences, I don't know where to look now here, sometimes they are clearly not quite optimal. So it does some funny operations which neither hurt nor improve the result. So for example, some bit flips that in total amount to nothing. So that can happen, and we as humans would see this. That depends a little bit also on my reward function. If I were to say that every extra gate it does incurs an extra penalty, then it would probably get rid of those. Yeah.
Srijit, you can ask your question.
Hi, am I audible?
Yes.
So this strategy works if you are doing a simulation, so you can calculate the overlap. But in practice, how can this work? You cannot calculate overlap on a real system. So only measurements can be done. So how could this kind of a strategy work in a real circuit?
Okay, yeah, that's a very relevant question. So right now we are working on simulations. My claim is that at least for the simple reward that I was talking about with the overlap, we could actually set it up that in a real experiment it would work. I would prepare a random quantum state that is known to me, not to the agent in the experiment. I would run the simulation, and then in the end, I could at least measure some expectation values or do some kind of quantum state tomography if I run it many times, and thereby evaluate the fidelity. So I think that would work in a real experiment. The catch is, and these are the fine print, so to speak, when we did this naive reward with the overlap, it turns out that this doesn't learn very well. So what we invented is a much more advanced reward, so to speak, that is able to tell me at each intermediate time step how much of the initially present quantum information is still there in the system, even though it has been distributed in a complex entangled state. Now, that is something that we could not easily extract from the experiment. So this is something that here we would really be stuck with training on simulations and then maybe implementing in the experiment, possibly slightly then still updating the strategy on real experimental data, but mostly this would work for well-characterized experiments. Yeah? But I will come back later to a experiment in another domain where we really take experimental rewards. Okay, I hope that answered it partially. Good. So you've seen us apply this to quantum error correction. We have other works about state preparation, stabilization, and so on. I will talk a bit more about quantum circuit optimization. But there's an obvious question related to what was just asked. What about experiments? So can we train in experiments? And that raises several aspects. So the first is, how can we extract the reward from an experiment? So you have to think carefully about that. And then the second thing is, if I think of things like quantum error correction, I want to be fast in my feedback. The agent really needs to respond rapidly because otherwise the qubit has already decayed. And so we wanted to tackle this and apply reinforcement learning with this real-time feedback on a superconducting qubit system in this case. And so we teamed up with a team of Andreas Wallraff in Zurich, and especially Christopher Eichler, who has since then moved to Erlangen, our place, and become faculty there. So to get the context, there have been a few works on doing experimental reinforcement learning in quantum computing. So I mentioned three here. The Birchuk group did some gate design over the cloud on a cloud-based quantum computer, improving gates. The Natalia Ares group did very nice experiments on the tune-up of quantum dots. And recently, you may have seen this in the Deboré group. There was a paper about a quantum error correction protocol for bosonic codes, and part of the optimization was done using reinforcement learning. However, in all of these, there was actually no real-time feedback with a neural network agent. And the reason is, of course, that this is challenging because, again, qubits decay very fast, and your neural network needs to be as fast as that. So what we were able to do together with our friends in Zurich was to have an experiment where a neural network is really not sitting on some PC, but on a field programmable gate array. It has been highly optimized, so every multiplication of a few nanoseconds has been carefully vetted whether it's really necessary. And it interacts with a superconducting qubit device where it takes in noisy measurement traces and based on those decides what action to take next, so which pulse to send down to the qubit. And it was optimized so that the overall cycle response time was less than a microsecond, which we believe is the fastest neural network agent that exists. Yeah? So beyond doing fine tuning of the FPGA programming, there was also a conceptual advance in the neural network architecture. So usually you feed in your input data and then step by step, layer by layer, you calculate eventually what's at the output of the neural network. However, what we decided to do was to feed in the first few nanoseconds of measurement data into the input layer, then calculate already the values of the neurons in the first hidden layer, and at the same time, the new measurement data rolls in. So all the time, you're simultaneously evaluating your neural network as well as receiving new measurement data. The price is, of course, that the last pieces of measurement data reach the output layer only very late, and there's only a single processing step still left. So the expressive power is a little bit reduced. But overall, this also means that the latency is very low because everything you add to the measurement data taking that would have to take place anyway, it's just the 50 nanoseconds or so that are needed for the last layer. So that really enabled us to have this less than 1 microsecond response times, this concurrent evaluation with taking the data. And once you have this, you can apply it to some tasks. And we really took, since this is the first time something like this has been done, the simplest possible task, which was to take a qubit and reset it to its ground state, because even if it's in a thermal state, it's not perfectly in the ground state. So the simplest strategy would be to measure it. And if it's not in the ground state, then to flip it. But then again, maybe your flip is not perfect and maybe the measurement is not perfect. So maybe you want to do it again. So that already leads to somewhat slightly more complex strategies. And if you have this figured out, then you can also apply it to things like instead of a two-level system, a 3-level system, so you take into account there might have been leakage to a higher qubit state, how would we then proceed? And in that case, what we did here in this plot was to analyze the strategy that the neural network acquired after some time. Maybe there's no need to go through the details here, but just some words about the training time. So what we do is, say we run about 1,000 trajectories. So these are action observation sequences. We run about 1,000, then we upload the results to a PC. The PC applies reinforcement learning algorithms to update a neural network. And then the copy of the neural network is sent back down to the FPGA so that the FPGA now has an improved neural network agent. Then it runs again for about 1,000, and then the cycle repeats. And within 3 minutes, you have really trained your agent to really successfully produce the ground state of your qubit. And then you can analyze the strategy. Here, for example, in the space of possible input signals, which has been simplified here, you would find that in this particular region, the agent always suggests to do a pulse that takes you between the second excited state and the ground state. And there are different actions that it can take as well. So yeah, we're very happy about this. And we are continuing, obviously, now moving to more qubits and different tasks. Okay. Yes, please.
You mentioned 3 minutes of training time.
Yeah.
How many measurement cycles is it like typically like a millisecond for each cycle of these experiments?
Okay, I would have to think. So I don't know the exact numbers, but
okay.
So this is, I don't know, maybe 10,000 or so in total traces that you're going through. Each trace consists of a few measurements and pulses. So that's what's happening.
Okay, so associated question is, so you mentioned the idea of maybe the initial state is in a thermal state. Have you tried by putting the initial state in some random other state, and does the
yes.
same strategy still work to go back to the ground state?
So what we actually did to improve the training was to deliberately put it, say, in a 50-50 mixed state or a 30% mixed state, if we take into account the higher excited state, because otherwise most of the trajectory would be, so to speak, very simple and immediately find it in the ground state, and then you don't learn very much. So it's actually smart to go to different initial states. Yes.
So how do you decide a hyperparameter in this situation? Like how fast your machine actually learns this in order to reach to the conclusion?
So you're asking about hyperparameters like the neural network structure or the learning rate and so on?
Yes.
Yeah. I guess trial and error in simulation. So we had already got characterization of the device, and my student, together with the experimental student, did a lot of simulations and then tuned up how many layers would be the optimal choice and so on. Yeah. But that's always an important question in any machine learning application and not so easily answered. The hope is that maybe whatever you pick as a reasonable first guess is not too far off from what you really need. If it's too specialized what you need, then probably you will not find it. Okay, so let me move on. Let me move back to the more theoretical level. And that's asking about more qubits. What I showed you in the beginning was 4 or 5 qubits, and I said it would be hard to simulate more. We have now our tricks to also really simulate more, but still at some point it becomes too complicated. You cannot use a classical computer to simulate a full-blown quantum computer, obviously. The question is, can we then, in such situations, still do anything if we can't simulate it? Yeah? One idea would be to run it directly on the experiment, but then come all the problems that I just mentioned. And another idea is something we introduced here. So imagine you have a quantum circuit that already does what you want it to do, but you're not sure whether it's efficient. Maybe the gate count could be reduced. Can a computer help us in doing this? And so there's actually a trick. You can introduce such transformation rules where you spot, for example, the sequence of 4 controlled NOT gates, and you realize you can easily replace it by 2 controlled NOT gates and still have exactly the same functionality of the overall quantum circuit. So there's a handful of such transformation rules. And now the idea is, given your quantum circuit, you can apply them without changing the unitary that the quantum circuit overall represents. So these are exact transformations. Therefore, you don't need to simulate the action of the quantum circuit because it's known that this doesn't change anything. And so we turned this into a reinforcement learning problem where now the input is a full quantum circuit. It has to be fed into the agent, and the agent has to suggest where to apply the next transformation rule. And maybe just briefly for those who are more into machine learning, how this is done technically. The quantum circuit already looks like a 2D image. So qubit number and time index are the two axes. Plus, you could say at each point, there is something like a color channel. So which gate is acting at the space-time point. And so it's really like a 2D color image that is being fed into a neural network agent and uses these well-known convolutional neural networks. And then the output looks similar. Again, it's 2D in some sense, and it has different channels. Now these channels correspond to different transformation rules, and the values in each of these voxels in this 3D structure, the values would represent the values of the policy probabilities. So the probability to take this particular transformation rule at this particular location, and then you just throw dice and pick one of those according to these probabilities. Okay, and we train on random circuits. So we generate random circuits, and we ask our reinforcement learning agent to compactify them by applying these transformation rules. At the beginning, it does just some random stuff, but it becomes better and better over time. And I skip some steps, but in the end, we are able to use it to improve relatively large quantum circuits. So in the background in gray, you see the original circuit, and blue is the circuit that has been transformed by the agent. And just a word about times. So this is a relatively large quantum circuit. If you apply a generic algorithm like simulated annealing to this and want to reach a certain level of performance, maybe you spend several days on doing this. Whereas for the reinforcement learning approach, yes, you also spend several days to train the agent, but once you have trained it, it will be good to optimize any arbitrary quantum circuit in a matter of hours. So once you do this more than once or twice, you win by doing the reinforcement learning approach because your agent has been turned into a kind of super efficient optimizer that can pick an arbitrary quantum circuit and immediately say where to apply the transformation rules. Okay. Yes, there was a question, please.
Native gates which you have to for a particular architecture. So does this take into account that constraint during the optimization that you are only allowed to use particular gates when you are?
Yes, yeah. So all of this, say, is done for a particular connectivity and gate set that also defines which transformation rules can be applied. And of course, the agent is specific to this gate set. So if you wanted to go to a completely different gate set or connectivity, you would train an agent again. Yeah. So when I say different quantum circuits, I mean, well, different quantum circuits, but all within the same gate set. Yeah. Good.
Just to clarify, maybe I missed the strategy behind. So you have shown these transformation rules.
Yeah.
Those rules are already defined.
They are defined by us. There's just a handful.
And
but
like,
the question is where and in which sequence to apply them. And that's what the agent learns.
but is it not, I mean, maybe I'm missing something here, that if you have a transformation rule, which means that it needs to identify that pattern and then replace it with a new pattern.
But
so
it's
what
not,
is there to
it's
learn
still not
here?
obvious in which sequence to apply, because sometimes it so happens that you don't want to be greedy. You don't only want to apply transformation rules that shrink you locally. You also sometimes want to apply rules that maybe expand you a little bit and then later enable you to shrink
so
even
it's
more.
It's a combination. So it's not a one-to-one change which is you're doing.
It's not just search and replace. Yeah.
And the reward here, are you checking that the updated state is still the same as the updated unitary is still the same as the original?
Yeah, we don't need to do that because these transformation rules are exact. That's the beauty of the approach. And the reward is simply the reduction in the depth or the gate count.
Okay, got it.
Yeah.
Are you able to check scaling?
Aha. So we don't have a systematic analysis of scaling, but this, for example, was trained on 10 qubit examples or 12 qubits. And it was immediately applied to 50 qubits. That's possible because we're using these convolutional neural networks that are also used in image processing and can, so to speak, scale up. And so at least applying this network to suggest the next action only needs, so if I move from 10 to 50 qubits, it's just by a factor of 5, multiplied by a factor of 5. So that's comparatively simple, the increase. Okay, good. So I don't know how much time I still have. 10 minutes, okay, good. So that should work out. So now I want to briefly come back to model-based reinforcement learning. What if we do know the Schrödinger equation applies to our world and therefore we can use it? And the basic idea behind this is in model-free reinforcement learning, the agent implicitly learns a model of the environment by interacting with it all the time and seeing, okay, if I do this, then the state of the environment changes in this way. But that also means a lot of training time is spent implicitly learning this model. It's much better if you do have a model already, for example, in a very well-characterized quantum device. So model-based reinforcement learning. And the angle I want to take here is to come from quantum optimal control. So you know probably optimal control. It started already in the 90s in the quantum domain, designing a good laser pulse to split a molecule or designing a good microwave pulse to affect a spin system, or these days to design good pulses to act on quantum computing devices. Now, the typical setting here is that you imagine inside your Hamiltonian, you have a field like a magnetic field or microwave field, and you can control the amplitude of this field as a function of time. And you want to find the best pulse shape that can, for example, produce a certain quantum state. Now, the most well-known generic numerical technique for this purpose is called GRAPE, gradient ascent pulse engineering, where you literally define what you want to have, like the fidelity of the quantum state and state preparation, and you do gradient ascent of this fidelity with respect to all the control field amplitudes. So that's the basic idea behind GRAPE. So you do direct gradient ascent. That's the state of the art. It has been used, for example, in microwave cavity state preparation. Here, that's an example, preparing a Fock state inside a cavity using the right pulse shapes that have been found via GRAPE. Now, what's the catch? Well, you send down a pulse to your system and hopefully it does what you want it to do. But as soon as you have some bath, some noise around it, then maybe there are better strategies. In particular, maybe there are strategies based on feedback, like the feedback that we already talked about. Why is feedback good? Because feedback means measuring something and then doing something in dependence on this measured observation. And that can be used to reduce the entropy, to extract all the entropy that came in from the bath. And so it's important for tasks like cooling or state preparation from a noisy initial state, or again, quantum error correction. And the catch now is that if you want to apply a model-based technique like GRAPE or gradient-based methods in general to this kind of quantum feedback setting, you have a problem, because at least if some of these quantum measurements are strong measurements, a projective measurement, it's obvious that it's not clear how to take gradients through this discrete event where you do a quantum jump to one or the other state. And so we set ourselves the task to combine these gradient-based optimal control techniques that work on continuous parameters with feedback, with the possibility of applying feedback to strong measurements. And so here's the situation. You would have your Hilbert space, you have your time intervals of continuous propagation of your quantum state, and then you take measurements and they lead to quantum jumps inside your Hilbert space. And the question is, how do you take gradients in a way through the whole evolution? So here's the same again. The yellow parts are the unitary evolution. They do depend on some control parameters, let's call them F. But then the tree splits, and your controls F, they should really be conditioned on all the past measurement outcomes M. So that's the setting we want to explore. And so here, just in a nutshell, is how this really works. What we really want to look at is a reward that defines how well we are doing. And we want to average it over all possible measurement sequence outcomes, because when I run it again, I get different outcomes, possibly. And then I again want to do direct gradient ascent, just like I do for GRAPE. But this reward being averaged over possible measurement outcomes contains two pieces, both the reward for a particular measurement outcome M and the probability for this outcome to arise. And now it turns out that both of these parts do depend on my control parameters. The reward, because it's, say, the fidelity with the final state, that depends on what was the unitary evolution, so what was the control. But also these probabilities, like psi squared, so to speak, Born's rule, they also depend on what is the wave function and therefore what were my control parameters. And so now if you take the gradient of this averaged reward, you will get contributions from both of these pieces. And if you work it out correctly, there will be a simple piece, which is just the gradient of the reward, averaged over all outcomes. But then there's a second piece that has this, if you rewrite it in a proper manner, this funny logarithmic gradient of the probability of a certain measurement outcome. And we want to again can write it as an average over measurement outcomes, which allows us to do Monte Carlo sampling over many trajectories. Okay. So there's some similarities on the mathematical front to the model-free reinforcement learning, but the difference is that here the probabilities we are talking about are really probabilities of outcomes for your quantum device, so they are not related to action probabilities of some agent. And now finally, in the last 5 minutes, if it's allowed, I will run through a set of example tasks. So we chose to apply this to a setting where we have basically a Jaynes-Cummings model, so a single atom coupled to a cavity. And we know that this is a very controllable model if you allow for qubit drive and switchable qubit cavity coupling. So we can, in principle, prepare arbitrary cavity states. But in order to also implement some feedback, we imagine that we add another qubit that is also coupled to the cavity and which is coupled in a dispersive manner. So you shift the frequency of the qubit depending on the number of photons inside the cavity. This is not completely invented out of the blue. There are systems that implement this Hamiltonian, and for example, beautiful experiments by Serge Bosch in the microwave domain. So the idea is there's a precession of your qubit Bloch vector that depends on the number of photons inside the cavity. And then if you do measure this ancilla qubit, you will learn at least a little bit about the state of the cavity. So that's how the feedback is implemented here. And then we can run through tasks. We first have to define what is where do our parameters enter. And we didn't want to do a fully continuous pulse shape, which we could have done, but rather we split it into different discrete chunks, each of which is parameterized. For example, here is the qubit drive with a certain drive strength. Here's the qubit cavity drive with a certain coupling strength. And here's the measurement where we can also control parameters. And we stack this multiple times behind each other. So there will now be many parameters that can also depend on the measurement outcomes. And so here just 2 or 3 examples. One task you can set yourself is purification. So you start from a noisy thermal state, for example. You want to create a pure state. You could do random measurements and eventually you learn enough that you become a pure state because you collapse to it. But it's much better if you turn to adaptive measurements. So depending on the previous measurement results, you change your measurement basis, then you can much more quickly go down to a pure state. And this is what feedback grape can discover for you. So that's this adaptive strategy here. Another setting would be state preparation. Again, you start from a noisy state, just a moment. And then the feedback grape can discover for you how to prepare, say, the cavity in a non-classical state by doing the right measurements and conditional unitaries. But there was a question.
Yeah, so does the result on the randomness, does it depend upon the which kind of probability distribution you are choosing, this random result?
Yes, so these maybe you're asking about this. So
yes.
These probability distributions depend totally on both the unitary evolution as well as on the type of measurement you're doing. Here I was imagining always, for example, measurements with discrete outcomes. We also have techniques of how to deal with measurements that would give you continuous outcomes, which is another thing you could have, where you have to proceed a bit differently technically.
No, are these probability distributions like the power law or exponential, this kind of distribution?
I wouldn't characterize them in this way. For example, if M is just discrete values, then it's just psi squared, the usual Born rule applied to the quantum state that has been time evolved. Yeah.
Okay.
So, well, I guess if M could take a continuum of values, then you could start asking the question you want to ask, and then it depends very much on the scenario.
Yes. Thank you.
Okay, last example, state stabilization. I would give the task, say, to stabilize Fock state number 5. And if there's a decay event taking me down to 1 photon less, then the agent will suddenly realize something is wrong, I should do something. And then it will do some crazy stuff and finally converge back to Fock state number 5. And here's one interesting aspect. If the control is implemented in the form of a so-called recurrent neural network, which is a neural network with memory, then we can train it on relatively short time sequences, but it will be good enough to also generalize to longer time sequences and stabilize basically forever by, so to speak, generalizing the strategy that it has learned. Okay, I guess that's already all that I wanted to show you. So I think reinforcement learning is really here to stay for the quantum technology, quantum physics domain. And there's these 2 branches that I talked about, model-free versus model-based, each with their advantages and disadvantages. So basically that's it. And here's a few references. Thank you very much.
Hey,
Any more questions?
Can I?
Okay, maybe we'll take the question from online. Is it Srijit? Go ahead. And after that.
Hi, thanks for the nice talk. So this is more of an academic question, sorry. So if I think of all various initial density matrices and various final density matrices that I can get through one of these evolutions, can that be represented by some Krauss expansion? Because it looks like some kind of non-linearity here. How does that? So usually, if I have a quantum system that's coupled to some environment, I can use some Krauss expansion to Krauss theorem to expand the.
I maybe didn't get every piece of the question, but are you, so to speak, suggesting an improved way of say, efficiently simulating the errors or the decay processes that could come about? Because what we're doing is simulate the full master equation, which the more qubits you have can become more expensive. You could imagine more something like a quantum jump approach, where you imagine there's only a few errors, and maybe that relates to your question, where you could then say expansion. Sorry, we cannot.
Yeah, Srijit, we have lost your voice. It's going in and out. Maybe.
Can you hear now? Hello.
Yeah, or you can type your question. And
okay, let me try once. Then I can type the question. So if I think of a usual evolution of a density matrix, I can represent it using some master equation or something. But here, when you couple it to a neural network, there is some kind of new non-linearity outside. So is the density matrix evolution still representable through some Krauss operator, Krauss expansion, or some master equation approach?
Okay, I'm afraid maybe this is a question you could send me by email or something, because the audio is not so good. So
yeah,
for me to understand.
Let's move on to one question over there. Yeah.
Yeah. So I had 2 small questions. So one is when you're talking about the policy, the neural network being the policy. So the reward function is being fed back into the neural network, right? So in a traditional sense, you'll have, let's say, something like Q-learning or an MDP process. But in this case, once you do the evaluation and assign the reward, that is being fed back into the neural. So the state select or the action selection is being done through by tuning the weights of the network, right?
Yes. So the reward function enters training in a very similar way as the usual cost function in supervised learning. So it's used to update the weights after maybe running a batch of trajectories. And then you get a neural network that will, on average, have a better reward in the future. Yeah, but so to speak, at any given run, the neural network doesn't get to know in advance what kind of reward it would get, so it cannot plan ahead in some way or something like this. Yeah.
Right, and just a small question is that in the case where you showed where. So I think in your first example where you were feeding in the data, but were not waiting for, let's say, the entire data set to go through. And then you are feeding in the next amount of time, let's say.
Yes, for the experiment, you mean?
So
yes.
When you do that, does that not mess with, let's say, your weight optimization? Either you're using gradient descent or Adam or something like that.
Okay. So actually, no. So the point is the training is done, say, on a PC using these typical modern frameworks like TensorFlow, and they are actually much more flexible. They can not only deal with the usual architecture where you feed into the input layer and then you just do step by step the different layers, but even if you come in from the side and feed in a little bit of extra input data at each new layer, they can deal with that. So they can take gradients properly through this slightly unconventional situation, and that's what we are doing.
Okay, thank you.
Last question.
Sir, what kind of optimization functions are you using? Like something like simple as a sigmoid function or a ReLU function, or like have you designed
activation
something?
functions?
Sir?
Yes,
activation
ReLU
functions.
and sigmoid and tanh, that is the typical activation functions we are using.
Yes.
Yeah. So.
Sir, I have a question for optimization.
Yeah.
Will you be using the same model for different set of circuits, or which is the one?
No, so here the idea is the same neural network can be used for many different circuits as long as these circuits are using the same gate set and the same connectivity. And we can even scale up the qubit number, so to speak. If it's a linear chain of 10 or a linear chain of 50, it will be the same neural network. That's the idea. Mm-hmm.
Yeah, there is a question from Zoom by Vikas Bhatt. The question is the neural network updated real time with experiments, or are the parameters fixed from simulations?
So in this experimental example, it is updated. I would not say real time. So we let it run, say, 1,000 trajectories. So that part is really real time. So with this 1 microsecond cycle and so on. And then we accumulate the data over these 1,000 runs. And then we feed this into a PC. We have, I don't know what the timescales there is. It doesn't matter so very much, but a second or so, the PC updates the neural network, and then the parameters of this updated neural network will be downloaded again to the FPGA, and then it proceeds. So there's always this 1,000 trajectories, then going to the PC, going back down again, and so on. So in that sense, it is done really during the experiment, but it's not real time in the sense of microseconds. Mm-hmm.
Right. If there are no more questions, let's thank Florian again. Thank you, Florian.